Melbourne, China. Okay, so shall I start? Okay. So we have talked about drying, which is the first stage of almost everything, whether you need to do pre-drying in a big separate dryer or a very small dryer right in at the front of your gasifier, if gasification is what is you are intending. Irrespective of that, drying is needed. So sometimes drying happens inside the boiler, which means in situ drying and then combustion. Then the consequence of that is that the boiler becomes very, very large. Or, as I said in the drying presentation, that pre-drying has a distinct advantage that you are removing the moisture up front. So that moisture doesn't have to go through the boiler and experience high temperature, and therefore a very rapid rise in the volume of it, and therefore the boiler volumes becomes excessively large. So that can be completely avoided. That fixed part as well as the operational and maintenance part is avoided if you do pre-drying. So that's an indisputable fact. So having done the drying, discuss the drying bit. Now I am going to this very short lecture on the introduction of combustion, but then the larger part will be the ash formation and the ash deposition, the fouling, and etc. So that will be the larger part. So let's talk about this first. If there is any question or more fundamental needs that is identified from this part, which is only 14-15 slides, then obviously I will cover it in one of the next presentations in the next few days. Okay, so most of you are familiar with the power stations, coal-fired steam power plants, right? This is how it looks like. Those who may not be, that's the boiler in here, the pulverized coal-fired boiler, I mean, that's in here. And this is the dust separation, electrostatic precipitator, or the back filter, whichever is the case. And then the coal comes in, goes to the coal conveyor floor right at the top of the boiler building, and from there eventually then it goes inside the through the mills, it goes other way around, from here and to the bunker, and then from there it goes through the mills at different levels of the main riser of the boiler. This is typically the slagging zone of the boiler. This is where the superheaters are located. Subsequent parts are reheat, and then the economizer, etc. And after that, the flue gas goes to the air preheater, whereby it gets cooled, but it gives its heat to heat the incoming air, both primary and secondary air, which goes in through the burners at different levels along with the coal, and then this is water. The rest is steam cycle. So I'm not going into that. So here, when we talk about combustion, we talk about the whatever goes on in here, in this part. So it's very, very typical, conventional PF-fired boiler, whether it is subcritical or supercritical or ultra supercritical or advanced ultra supercritical. This is the neck that is deliberately kept in order to get the velocity up, so that heat transfer is much better, and also the deposition is hopefully less, because if there is a low velocity, that there will be a lot more deposition. We'll cover that later on, but typically that's what you will see. There will be neck, and then the second pass is straightforward vertical. Okay. So when you talk about combustion, everything that takes place here, that's what combustion is. So again, the distinct processes, as I mentioned before, are the drying, and then the coal then gets pyrolyzed, and then the ignition of the pyrolyzed solid product, which is called char, then the combustion of the pyrolyzed product, the gaseous pyrolyzed product, which is the vapor, or the volatile matter, and the combustion of the residual char. So these are the distinct phenomena that take place when we, in aggregate, call the combustion process of solid particles inside a coal-fired boiler. So the way it then happens sequentially, if we describe it in this way, with the x-axis being the residence time and y-axis is the temperature. This is only, this diagrammatic representation is only for PF-fired boilers, not for fluidized boiler. The time scale will be different. The x-axis will be completely different for fluidized bed. So this is your PF size, 10 to 100 micron. 10 micron is not necessarily always preferable, but that's a fact of life, that you will always get fines. So anything in that region, they during the drying process, whereby it is heated, they give up the water vapor, the moisture in the drying, everything, hopefully. Correct. Correct. That time it gets warmed up to some extent. So what? Not completely. So this is the meal here, this combination. So from the bunker, the bunkers are located at about say 30 meters, so that sort of level. And the whole boiler is hanging from the top. It's supported from the top so that it expands down in the bottom direction. And in here, it is then it is then transported, the further milled ones, it transported with air, primary air, but it is heated into the boiler, into the through the different burners at different zones. Here, typically, they have shown 3 different levels. Sometimes the burners, depending on which company is providing the boiler, they will have opposed burners, or they will have single. Depends on the diameter, the cross section of the boiler. Obviously, the larger the unit, the larger will be the diameter, and therefore you will have to have opposed burners, okay, from opposing sides. So the fireball is right in the middle, and it's tangentially, the swivel is allowed, deliberately allowed to the air, so that it carries the particles together with it, and then swirls around, and during that process, the 10 to 100 micron particles, they get combusted. So here, to some extent, drying happens, but not much. Predominantly, it happens here straight away. So if we look at the time scale, x-axis, you can see that the fraction of a second drying happens, and it happens purely because the particles are very, very small. That's why. If the particles were millimeter size, it would not have given up its moisture that easily within 1 second, far from it. So, and that's an important thing, I'll come to that later on. Then, near the burner zone, so the burners are from the sides, near the burner zone, but inside the furnace, you then have the pyrolysis happening. So what's happening is that the dried coal particle is giving up its volatile, depending on and how much volatile it will give, depends on what temperature you are running it. And I'll come to that a little bit later, just to remind me, if I forget, about the temperature. So it's giving up its heat as it is spiralized. Sometimes it is also called devolatilization. In that process, what happens, these minerals which are in the coal to start with, they are starting to become ash. As I mentioned right at the beginning, coal has minerals, coal doesn't have ash as it comes. It only gets, the minerals get converted to something which we call ash. So it becomes only ash here. And then during that process, there is also the fracture of the particles, because as you can imagine, it's going straight into a hot atmosphere. So immediately they will experience a thermal shock. As a thermal shock, the coal particle will disintegrate like anything, very, very quickly. So that happens between, so this is, the scale is milliseconds actually. So drying here is extremely fast because it's happening at a very high temperature. Devolatilization is also of the order of 100 milliseconds. So it's giving up its volatiles very, very quickly. At that point, what remains is the devolatilized, all the pyrolysis vapor gone, and the solid product, which we call char. And that char has become, as you can see, is very, very fractured. It has lost its volatiles, so essentially it has lost 50% of its mass, roughly. That's the typical volatile and the moisture content in a coal particle as it goes, more or less 50%. So that's why the 50% burnout, that's where it comes from. And then in here, this is the burnout zone. It is not in the near burnout zone anymore. It is away from the burner, and you want it deliberately to happen. The char combustion, you deliberately want it to happen away from the burner zone, because during the char conversion, it is giving fly ash, because it flies away. That's why the term fly ash. And you don't want that fly ash to be depositing on top of your burner, because then the burner will then start losing its effectiveness. Okay. So that's why everything happens away from the burner in the burnout zone. But look at the time scale. You are deliberately trying to make everything happen in this much milliseconds. So, so it's about a second. So in a PF-fired boiler, in the furnace zone, which is here the burner are more or less in here, you want all the heats to be released there, so that everything that goes above that, where your steam generating tubes are, going to the high pressure turbine or the IP turbine and eventually the LP turbine, etc., they are seeing maximum amount of heat extracted from the coal particles, char particle through and the combustion process is complete. You don't want any combustion to happen on the surface of the tubes at all. That's how it is designed. So in order to do that, you need to know the coal very well. You need to know, okay, how long the coal particles will take to undergo that. Testing can reveal it, but more or less this is now very well known fact to the technology developers. Unless it is a very unreactive anthracite kind of coal, which will not work well at all with this type of burner arrangement, pretty much this is very well known. You give them the coal composition and the coal rank, the technology developers will immediately tell, I'll choose this design, not that design, etc. It's that simple. It's very well known now, because it's 50, 60, 70 years of history behind it. Yeah. Yeah. Anthracites are the most mature of coals. They have stayed in the ground at high pressure and temperature as well over millions of years. So the coal structure has become very compact. It's not pore or anything. Anthracite is almost like the lead in your rubber, in your pencil. I mean, it's that compact. you cannot, first of all, you cannot gasify it. You can only combust it. But even to combust it is a challenge. So in many countries, there are lots of anthracite. And it can be used for some other purposes, but for power generation, you need a completely different type of boiler design. It's called a down-fired boiler, as it is called, as opposed to horizontal multi-burners, opposed to multi-burners. So anthracites are very unreactive, simply because they struck. True. Pure, I mean, depends on your definition of pure, but is the most mature of the coals, I would say. Okay. So in terms of, it's actually an irony. The lower rank coals are more reactive than the higher rank coals, simply because they still haven't become mature. So it's like just a young kid, you can tailor it to become whatever. So brown coals, lignites are like that. They are not mature. They are somewhat unstructured, so you can train them to do whatever it is. That's the pure similarity, as simple as that. You cannot do that to anthracite. Anthracite will resist. Okay, so age of the coal, which means the rank of the coal. By age, we mean oxygen content in the coal, the very open structure in the coal, so there are a lot of pores, so that the oxygen can go inside the pores and can react with the carbon to give you carbon dioxide, rather than waiting to react with the carbon from the surface, shrinking the core and then gradually eating the carbon from outside in. Whereas if it is an immature, low-rank reactive coal, the oxygen can actually go in straight away, inside. So it can eat the carbon inside out as well as outside in. It's that simple. In the anthracite case, because anthracite is very well structured. Anthracites are used, I have seen in Spain, anthracites are used in power generation, but it's a very difficult burning sequence. It has to be very, very fine, first of all. It has to be very, very fine, even less than that, but more importantly, much, much higher temperature. So that's what it is. So people tend to avoid anthracite for power generation if they can avoid it. How is oxygen present in the first place in the coal? Okay, so that comes from the biomass itself. So if you take a piece of biomass, even though through the photosynthesis process it is, absorbing the CO2 and eventually releasing the oxygen, but then by the time it has gone through the qualification process by going underground and it is subjected to pressure and temperature, etc., it is no longer doing the photosynthesis process. So whatever oxygen was with it at the point of going to underground, that oxygen stays with it. Now, as years go by, by years it means hundreds of thousands of years. Young coals are only about 90,000 years old. So as years go by, the structures become more, the coal's structures become more and more structured, if I may say so. And carboxylic bonds groups are one of the easiest groups to break. A little bit of a heat, you can break them. So that over a period of time, when the coal has gone underground, a lot of things have deposited on top of it, the overgrounds and etc. The pressure and the temperature eventually breaks the oxygen down, releases outside, it then loses its oxygen. So anthracite has got very little oxygen. After that, bituminous coal has got more oxygen. Subbituminous has even more oxygen. Lignite has got even more oxygen. That oxygen, for combustion point of view, it is a welcome element. It's welcome because technically you are not supplying that amount of oxygen for the carbon to react from outside. So supplying air from outside to the combustor comes at a cost. So it has plus and minuses, but at the same time, if you have too much oxygen, then also it creates other problems. And we'll see that in gasification what happens. If carbon dioxide production is the objective, which is for combustion based power station, because you need the C plus O2, that exothermic reaction to happen and give a lot of heat for the water to become steam, then it is oxygen is not a problem. But if it is gasification, it's a different problem, but I will deal with that in more detail. To some extent, yes. Okay. So because you have raised the issue of catalyst, that's an interesting issue. What are the catalytic elements in coal or biomass? Can anyone tell me? Yeah, absolutely. Sodium, magnesium, calcium, potassium in biomass, these are all catalytic elements. But of course, phosphorus. But these are not present as individual elements. They are present as minerals, as compounds with other, in conjunction with other elements, right? Catalysts don't like temperature. Catalysts work quite well, 300, 400, 500, 600 degrees. After that, the catalysts, they die. They don't like temperatures. They die simply because they lose their activity, independent activity to catalyze the reaction. And when temperature increases, temperature dominates everything. Temperature together with oxygen can eat out steel, can eat out, titanium, for example. You don't need catalysts. Where catalysts become a lot more important is actually in gasification, which is a slow process. Sometimes it is a low temperature process, such as fluidized bed or fixed bed. That's where catalysts, the mineral, the catalytic effect of the minerals can be significant. As far as combustion is concerned, catalysis is not important. So here we are. I'm talking about the time scale in here. So you can imagine in the boiler, in the combustion, everything happens very, very fast, 1,000 milliseconds. That's why I have been saying right at the beginning. The combustion is fast, gasification is slow, and you will see what time scale we will use when you talk about combustion, gasification. Sorry. Important thing to know from your point of view, that this is fast, this is this is what you want to happen near the Burnout zone, and the hydrodynamics has to be designed in such a way, the boiler designer designed in such a way that everything is elutriated away from the burner immediately after the coal has paralyzed. That's a design issue. That's fluid dynamics. You can predict it quite well these days through computational means, CFDs, okay? Computational fluid dynamics. That's not a problem. Other important aspect in here is the temperature scale. So you can see that by the time the coal is dry, the coal has become, within that time, for that particle size, it has already experienced a temperature of about 400 degrees or so Celsius. And then by the time it releases its volatile matter, its temperature has gone quite high. inside in the near the Burnout zone. So, it is very intense, very high. And after that, the char conversion, there is no more heat release, and therefore, the temperature gradually decreases, and that is what you want it to happen, so that the fly ash does not experience high temperature anymore, because fly ash is nothing but the minerals converted into something else. And if you allow that mineral to experience high temperature, they will become glue. They will start sticking onto the surface. That will impede the heat transfer from the surface to inside the water, and therefore, your heat transfer and the generation of steam will be affected in a negative way. So, you want the design of the boiler such a way that as soon as fly ash is generated, majority of the carbon is gone, you want the fly ash to drop its temperature quite quickly. That is why you have there the reheaters, the economizers, the coolest temperature feed water going in, so the fly ash gets cooled there quickly, so that it does not become deposited much. Still, it is not avoidable, but at least it should be manageable. There are other ways of managing the deposits inside, and I will talk about that in the next presentation. One important thing in here is this. I talked about the proximate analysis and the ultimate analysis. This proximate analysis and ultimate analysis. So, this is denoted as the coal is classified with a moisture, volatile matter, fixed carbon, and ash. The total should give you 100. And here, moisture stays at moisture, ash stays at ash, as ash, exactly. The volatile matter and the fixed carbon is supposed to be carbon, solid carbon. So, fixed carbon stays at predominantly as carbon. The volatile matter is a mix of hydrocarbon and everything else. So, it is carbon, hydrogen, nitrogen, sulfur, and plus this additional carbon from fixed carbon goes in here. So, these two, and obviously total is 100. And oxygen is by difference oxygen. Oxygen is not measured directly, it's all added up. So, carbon, hydrogen, nitrogen, sulfur, and ash are measured and then added from 100 to give you the oxygen content. So, these are two very important measures, and then as I said before, before the lunch, then we separately find out what minerals are present in the ash. So, the ash analysis, as it is called, is actually the compounds of silicon, aluminum, sodium, calcium, magnesium, potassium, titanium, few others. But you will see in the ash analysis that these are expressed as oxides of these elements. So, this is how they are expressed. TiO2. So, titanium. But in ash, sodium is never present as Na2O. You will never find Na2O. This is just a convention to represent the presence of these elements in oxide forms for just as a convention. Silicon is present as silica, but silicon is also present in conjunction with sodium as sodium aluminosilicate, etc. So this is just a convention, nothing else, for the benefit of calculation. So these three together are extremely important for the boiler manufacturers to give you the design of a boiler. They calculate the boiler size, the near burnout zone, how long that should be, the actual burnout zone, how long that should be, what should be the volume, what should be the residence time there. They design it as soon as you give them this bit. What is also important, more and more these companies are asking, as I said, the silicon is not present as silica. Silicon is present as in conjunction with the other elements in this type of things. But once you measure this, X-ray fluorescence is a technique widely used to measure this type of analysis. ICP, inductively coupled plasma with mass spectroscopy, ICP-MS, or optical emission spectroscopy, ICP-OES. They are complementary. Chemists know it very well. Through LIPS as well, so a little bit more complicated, and it gives a far more accurate indication of sodium, the alkali matters, elements, than anything else. So these are the predominant techniques analytic techniques to measure and give you an indication of this, the ash analysis. But there is something else that is also very well now known, and X-ray diffraction. What X-ray diffraction does is it only identifies the crystalline compounds in the ash. So you have the coal, thermally processed it, mineral matter has become ash, and hopefully some of the ash constituents have become crystalline compound. Not all, some will be amorphous. A lot of them will remain amorphous. Amorphous compounds are not detected well by the X-ray diffraction at all. They will just come up as a blob, big blob. But X-ray diffraction, the crystalline compounds will come out as a sharp peak, and comparing with the library database, you can say that this is the peak for silica, and this is with my baseline. If I compare it, exactly this much silica is present, exactly this much sodium silicate is present, exactly this much sodium aluminosilicate is present. Point I am making is, all of these are measurable by complementary analytical techniques, pretty well established, and standards exist. Some of these are not necessary for combustion-based boiler plants, but for gasification plants it's extremely useful to know the X-ray diffraction-based analysis, crystalline compounds, and why, I will see that. But the other important thing is this volatile matter that we have in here. It's not a fixed number. The problem is, if you take a chunk of coal, if you hit it, it will start giving its volatiles. The more you hit it, it will give you more volatiles. So at 500 degrees, it will give you X amount of volatiles. At 600, it will give you Y amount, then Z amount. And if you take it to a higher temperature, it will give you even higher. So volatile matter is not a fixed quantity. Depends on what temperature you are measuring. So there is a standard, worldwide standard, that's Indian standard as well, that you do it at 900 degrees centigrade for 7 minutes in closed crucibles. So you take specially designed crucibles, these are pretty well designed, with leads on it, and the standards actually tell you how much coal you are allowed to put inside. And then you heat up the furnace at 900 degrees, preheated, load the coal, designated amount there, cover the lid, put it, close the furnace. So keep it for 7 minutes, switch it off, bring it out, take the weight difference, and it will give you the volatile matter, standard volatile matter. But the point I'm making is that 900 degrees, 7 minutes. The important thing is you have to put only a designated amount, because if there is more than designated amount you put, then there will be too much volatiles that will be released, as you would expect. More coals means inside means more volatiles, therefore more pressure rise. So the bubble, the cover will go off. As soon as the cover goes off, the volatiles come out, they get combusted, they then also burn the carbon. So you will get a artificially inflated value of volatile matter. So volatile matter measurement is quite tricky, but unless you know it. Okay. So depending on the coal type, you may or may not need to go into that sort of temperature, and therefore how much volatiles are released, that will be affected, and that will be affecting this much, this step in here. So from a modeling perspective, you really need to know all of these in here, that what is my standard volatile matter, standard fixed carbon, standard ash, etc. You will only design it on that basis in the modeling. And then your methodology will be right. So let's go to the next slide. So here we have I have copied something from the book by Hartmut Spleitoff. If it is a fixed bed firing system or fluidized bed firing system, or a pulverized PF firing system, obviously the particle size varies, micron to millimeter, as you can see, and that makes the heating rate different. What is heating rate? Is when you put the particle, say in PF fired case, you put the particle inside the boiler, you are subjecting its surface to be heated, and therefore there is a gradient of heating rate between the surface and its core, the center. So temperature difference of that is actually the heating rate that it experiences. Smaller the particle, as is the case for PF fire, higher will be the heating rate, as you would expect. So that's what these numbers signify. Larger particles, they will experience lower heating rate, and therefore their performance in giving up the gases, the volatiles and the char, etc., will be different. That's what every system is dependent on, its particle size that it handles, the heating rate that it experiences, and of course the time that it experiences for drying and pyrolysis, time that it experiences for the volatile matter to be combusted, and time it experiences for its residual char to be combusted. So say, for example, you have a very small particle, and you just drop it in a heated environment. It will experience a heating rate, very fast heating rate, because it's very small, right? So very quickly it will get to the temperature inside the environment. So that's what the heating rate is. At what rate it is getting heated close to the temperature inside the heated environment. In fine particles, it gets very, very quickly, as you can see, because the heating rate is, that's, normal expectation, right? Okay. So I draw your attention to these 3 columns in here. This drying and pyrolysis period, time experience, and time experience for residual char combustion, and this column they have conveniently kept it blank for a reason. The reason is it all depends on how much volatile is there in the first place inside the coal. If it is an anthracite, it has very little volatile, practically nothing. If it is bituminous coal, it is a bit more volatile. Subbituminous, more. Lignites or the brown coal, almost 50% of it is volatile. So that's why it is black. But volatile combustion is essentially fast, of the order of 1 or 2 seconds at most. Theoretically, you will see between this and this point, between here and there, where you expect all the combustion to be completed, you are looking at only a couple of seconds at most. Therefore, pre-drying the coal to the right moisture level, milling it to the right size is extremely important, because you have designed your boiler accordingly, and all on a sudden, 2 years down the track, a new operator comes, a new mining company comes, the operators change, they say, oh, I don't care about the boiler anymore, I'll just do it as simply as I can. They start milling it to a coarser size, they start pre-drying it to a lesser extent, the boiler gets buggered completely. So it's very important that the operators also know a bit of all of these things. Who keeps track of all of these important issues will be people like you, who will be in the supervisory capacity. You will have the fundamental understanding of what is important and therefore what needs to be maintained. Okay, so here what I have done is I have copied a few things from this and the important places. What I think is important from a practical perspective. I haven't gone into the equations of this, how these were drawn. These are that can be found in this literature. But the important things to understand is, if it is a brown coal, that's a highly reactive coal, versus a bituminous coal, it is less reactive, but not as less reactive as anthracite. That as a function of time, how much weight it loses. Weight loss happens because of the combustion. And you want DAF in here stands for dry, ash free. So moisture free basis, ash free basis. What remains? What remains is moisture and ash gone. Only these are the combustible, two combustible constituents. You want only those two in here. That's what dry ash free basis means. So the point in here is that as temperature increases, you can get the very high weight loss or high burnout at a very, very short period of time. So that's how you will read it, rather than looking at the individual values. So it is simply a function of the particle size. It is a function of the coal rank. That means its reactivity. That means how mature it is or how aged it is. It gives a reasonable indication of how long the drying and pyrolysis will take, how long the char combustion will take, depending on whether the coal is this type or that type, and particle size is PF size anyway, 10 to 100 micron. Yes and no. So see in here, this particular, I actually haven't gone through, I know you are basing on these two temperatures in here. This brown coal, I suspect it has got more ash in it compared to less moisture but more ash in it. But otherwise, the way to see it is, interpret it is that as temperature increases, or as temperature increases at a particular time, you will get more and more weight loss when you increase the temperature. So some of this you'll really have to go into the nitty-gritties of what coal that they use. But this, I know you are basing it on these two figures in here. Seems to be a bit anomalous, but the way I would interpret is, at a particular time, what happens to the burnout or what happens to the weight loss as temperature increases. So that's how we should be looking at it. Even there is a difference between some lignites, for example, has got very high ash but low moisture. Some lignites have very low ash and but very high moisture. So our brown coal, for example, only has 2% ash when it is fully dried. But when it is not dried, it's got 60% moisture. But it is extremely reactive. On the same token, the German brown coals, they have got, when they dry it, they have got about 6% ash, but fully dried, but they are slightly less reactive than ours. So they take longer time to completely burn out, and therefore that's how their boilers are designed as well. But if you look at just the numbers in here, they can be a little bit confusing, anomalous. The way I look at all of these figures as they are presented is that at a particular time, whether at this time or that time or that time, unless you significantly increase the temperature, you will not get high conversions. You will get high conversion at a short period of time only if you increase the temperature considerably. Whether that is beyond a certain temperature, brown coal and bituminous coal, no difference. Temperature overrides everything else. Correct. Yeah. So what will happen in here, in this case, what will happen is that because the brown coals have got very moisture plus ash content compared to bituminous coals. Bituminous coals, moisture plus ash content is less than the moisture plus ash content of the brown coal. So technically they need a little bit more time, the brown coal, in order to get rid of the moisture plus moisture content in particular. But also when you want to get rid of the moisture content, you also have to have the ash content raised to the same temperature as well. So that's what this curve, this box or this figure actually means. Even though it is for drying and no, this is entirely for the drying and pyrolysis. This is not for the char combustion at all. These two boxes are both for brown coal. Char combustion will also take place, but that's not being shown here. Here, no, they actually did it. Yes, they did it under, yes, that's right. They did it under just pure pyrolysis condition. Yes, that's right. That's right. So if you look at these ones in here, they are, say, this is 1940 Kelvin. So at that 25 milliseconds, sorry, they have roughly 50% loss. Here you will see this particular case, 25, is more than, slightly more than 50%, perhaps 55% loss. So I think it's very, very difficult at that high temperature to completely differentiate between the different ranks of coal, because temperature dominates everything. Correct, correct. At the lower temperatures, yes, that's right. And these are not pre-drying cases at all. These are all in situ drying experiments that they did. These are very early but well accepted set of experimental results from the Japanese. In the pyrolysis should not be, because that, okay, the oxygen that is present here in the coal, it's actually not present as elemental oxygen at all. It is present as all these different bonds in here, C, O, then H, O there, so the carboxylic bonds, carboxylic groups. So the oxygen is shown as an element here, but actually it is not elementary oxygen that will come out. When you hit it, it will come out together with some of this carbon as CO2. So this carbon will no longer need any oxygen coming to the primary air or the secondary air. So you'll need less oxygen to be supplied. So when we do the stoichiometric calculation to find out for a given ultimate analysis how much air is to be needed, we subtract this amount of oxygen in here, because the understanding is that this oxygen will take out some of the carbon as the bonds break. The oxygen will come out as carbon dioxide. Yeah, so oxygen will come out as carbon dioxide. So volatiles are the gases of carbon, hydrogen, nitrogen, sulfur, etc. Never come out as elemental oxygen, never. So it will come out as CO2 predominantly, and to some extent CO, correct, and to some extent NO as well. And if you and then that NO can become NO2 later. Yeah. Okay, so the way it happens is, no, this oxygen is not present as fixed elemental oxygen. It is present together with the bonded to the other oxygen as the covalent bonds, and in conjunction with the carbon. So it's simply breaking the bond here at that point, and that's how it is going out. So it's not reacting with the carbon to give you carbon dioxide. It is the breakage of the bond. So coal is often denoted as CX, HY, O, Z, and SN, S something, and something. So these are the easiest ones that they have affinity towards each other, and that's how they come out. It's carboxylic groups, COOH groups. And together with the COOH groups, you also have the minerals associated, the sodium, silicon, aluminum, etc. And that's why those minerals eventually will also take away some of the oxygen that is present in the ultimate analysis oxygen. So oxygen is never present. None of the elements are ever present alone except for this fixed carbon, which I don't.
Can I say that this oxygen which is present in both comes out as a pyrolysis product rather than a combustion product? Even if I am cooking it as a combustion, can I say that it doesn't participate in combustion even though actually this oxygen is there, it comes out as
Absolutely. True. So technically, if you take a piece of coal and then continue to heat it and heat it and heat it, take it to the high temperature for a sufficiently long period of time, then all you will be left with is some amount of fixed carbon, very pure carbon, or almost pure carbon, plus the ash, nothing else. Nitrogen will be gone, hydrogen will be gone, oxygen will be gone, mostly sulfur will be gone, together with something else, ash and the carbon will be. With respect to gasification, lignite is more reactive with respect to gasification. Lignites are usually more reactive than bituminous, subbituminous, and of course. Now, okay. So, when we say they are more reactive, reactive means in relation to a reaction of particular time. So, what's the reaction? One reaction is CO2 forming reaction, which is combustion. Other one is CO reaction, which is related to gasification. So, it relates to combustion reactivity or gasification reactivity or both. I don't think that in a PF environment where a fine particle is exposed to a high temperature very, very quickly in the fraction of a second, in milliseconds, the devolatilization reactivity or the pyrolysis reactivity varies significantly between lignite or bituminous coal, not significantly. It is in the subsequent combustion of the fixed carbon with the oxygen or gasification, again carbon with the oxygen or carbon with the steam for gasification, that's where the reactivity issues will come in. That's where the coal rank is. Not that much in pyrolysis stage. Correct. Absolutely correct. So, and this is, I mentioned that the importance of standards in determining the volatile matters, 900 degrees, 7 minutes, 900 degrees for 7 minutes is the internationally recognized standard. Otherwise, you will be getting a lot different values. Sometimes people report volatile matter based on TGA, thermogravimetric analysis results, where the time is very, very long. Important thing is it doesn't conform to the standards, accepted standards. But the other important thing is, as long as you are consistent and transparent in your reporting that this is how I am reporting it, it's fine. But as long as you keep it. I have kept it for 1 hour, it still was losing its weight. So So how much total volatile is present inside the coal, that depends on what your reactor is, because your boiler will never see more than will give more than 2 or 3 seconds to the coal before it starts to cool down, everything is combusted. In the gasifier, depending on whether it's a fixed bed gasifier or fluidized bed gasifier, you'll be getting several minutes, several minutes. N-train flow gasifier, 7 to 8, 10 seconds maybe. So within that period, whatever comes at that temperature is important. But for the engineers to design, they need to know a certain number based on which they will say, okay, if you tell me how much volatile is present at 900 degrees for 7 minutes, then I can tell you from our experience, in-house data, etc., how much volatiles will be released at 1500 degrees centigrade for 7 seconds. So the important thing is to report everything based on a certain standard. Then everything else can follow. But to answer your question, that how much total volatile is present in the coal, no one knows. Perhaps one has to do a very, very long experiment for academic interest's sake, and then find out when the volatile matter release has completely ceased. So, for example, if you do what is called a thermogravimetric analysis, wherein this is the weight percent. So you start with 100%. So you will see this type of curve. This is time at a particular temperature. Say this is at 900. What this means is, if you taken a certain amount of coal, subjected it to a temperature of 900 degrees, you will see this type of curve, that it first loses its moisture here, and then it loses its volatiles between this point and that point, and then it starts losing its weight, or its weight stabilizes, and it doesn't lose any more at that particular temperature. If you do it at, say, 1000 degrees centigrade, it will be faster. It will go like that, and then it will be going like that. If it is 1500, it will go. It will lose its moisture even faster than this, and then it will go like that. So then the apparent dilemma is that, what will you report to the designer? The important thing is, all the standard organizations have decided that let's report it on the basis of 900 degrees and 7 minutes, and then everything else can follow from there. Oh yes, absolutely. In fact, in the near the, if you do the CFD modeling, you will see a lot higher temperature than that. And well, in the fireball region, you will get 1700 degrees easily. But you can control that by bringing in air, because you don't need very high temperature, because the ash will then start creating havoc. It will start melting, and then it will clog up the bottom of the furnace. So you moderate the temperature there by bringing in more air. So if it is a very high volatile coal, for example, then you will have to have more air to moderate the temperature to a limit that will ensure less slagging, less melting of the ash. So when we go to the next presentation on the ash fouling, ash slagging, that's where it will become a little bit clearer. And here also I have taken from the similar batch of people, Douglas Schmoot and Ian Smith, the Australian pioneer. They did a lot of experiments looking at drying and pyrolysis together in a standalone reactor environment with different types of coal, Victorian brown coal versus bituminous coal, and then they pyrolyzed it at different temperatures from this and that, about 1200, 1400 degrees Celsius, and then they started measuring the how much remains. So this much remains beyond a certain temperature. It doesn't lose any more of its weight. The weight stabilizes. But also, most importantly, what gases come out as temperature increases during the pyrolysis process, not during the combustion process at all. So no additional oxygen supply. Important thing to note in here that in these zones, they will get the tar, which is the very higher order hydrocarbons. And then you will get, of course, from the breakage of the carboxylic bonds, CO and CO2. And you will get the other hydrocarbons, so for example, methane, ethane, propane, etc. But you can get very large hydrocarbon molecules, which are extremely viscous at room temperature, which is called tar eventually, and more of it if the coal is bituminous coal, less of it if it is brown coal. So the way I read at this is everything starts from 100%, and then as a function of temperature, how much char actually remains, solid char, fixed carbon remains as temperature increases, if it is a bituminous coal versus if it is a brown coal. So that's the bottom line in here. Well, and if you take a completely different type of coal from another mine, you may get similar trend, but the figures may vary. From engineering perspective, the most important thing is to know, do we get any significant amount of tar or not? If we get any significant amount of tar near the vicinity of the burner, because that's where the pyrolysis takes place, then you will have to have ways to break the tar down, and the way to break the tar down is to inject more air through the swill so that it quickly breaks the long chain hydrocarbons into smaller chains. That's how it is done. At what rate you are going from 200, from the particle's point of view, at what rate the particle is going from 200 to 400 to 600 to eventually the gas temperature, that will be dependent on the nature of the particles. Nature of the particles means what's the size of it. The finer it is, quicker it will go. Irrespective of that, if it is in the PF size 10 to 100 micron, from brown coal to bituminous coal, it's not going to matter all that much. So it's not cycling, temperature cycling at all. It's just seeing one rapid temperature rise.
So you mean whether it is temperature with respect to time is going to be almost similar?
Temperature is an overriding influence has an overriding influence on the pyrolysis performance. Nah. I actually don't. I think it's a lot less. So these are not standard proximate volatile matter. same amount of time and same particle size. Only the difference is two different types of coal, and they wanted to see whether there is any significant effect on the coal type on the drying apart. More or less. In this case, yes. In this case, the char, almost all, you are not extracting any more volatiles because its weight has stabilized for this particular coal. But if you look at in here, they haven't gone to 1200 at all. They may have stopped simply because they could not go for whatever reason. But around the same mark, it has stabilized, you see. But the figures are slightly, this is about 50, and this is also about 50. Yeah. So what? Yeah. So how much fixed carbon is present? That also depends on the temperature, because if you increase the temperature and keep on maintaining the temperature long and long and long and long, some of the fixed carbon will migrate to volatile matter and then will be released. So that's why it is extremely important for the designer to know the figures at a standard condition, which is 907 minutes. And everything else can follow from there. No, initially everything was 100, and then at the end, what you are left with is this much char. No, tar is not 100. Tar is somewhere between here and there with long chain hydrocarbons. Total gas is between here and there, and then the other gases are between here and there. That's how you need to do it. Okay, so so the next bit is the particle then needs to reach its ignition temperature, the solid char particle that remains after the volatiles have been extracted to the maximum possible extent. At that condition, the particle then needs to reach its ignition temperature. It also has to have access to its oxygen. So you supply the air through the primary air system or the secondary air system higher in the boiler region, so that the char actually gets, as the char gets from the coal, it gets converted from the coal. The coal releases its moisture, then it releases its volatile matter as much as possible. It then gives up its char. The char has to have access to the oxygen. So char oxygen, access to the oxygen is extremely important for the char. So the way, so these are again, I have taken from Splithoff, but he took it from Stahlhelm. So there are different classifications for ignition and for the char combustion stage, or leading to the ignition stage, stage 1, stage 2, and stage 3. They're calling them ignition and volatile burnout. So volatiles have been released. The volatiles will obviously see the oxygen, and any competition between the volatiles and the solid char for oxygen, volatiles will always win. So the volatile burnout happens quickly. That raises the temperature as well near the vicinity of the particle, which then gets heated up as a consequence, and the particle then ignites. So these are the three steps shown in here. As they ignite, the volatiles combust, then the char remains, more volatiles released, that then the char then gets combusted, and essentially it loses its carbon content as much as possible before converting, remaining only with ash and nothing else, hopefully. Maybe 2 more slides, and then we'll take a break. That will then seamlessly go into the next one. So, so in here, what has happened, this is the particle size is the x-axis, and the heating rate is on the y-axis. And these are the heating rate experienced by the char particle, not by the cold particle anymore, because devolatilization has taken place. And this is a very standard curve. Sometimes the boiler designers want to see that where these different regions are. Here, zone 1, zone 2, zone 3. So these are that zone 1, zone 2, zone 3. Here, it is zone 3. Happens when for this type of particle sizes. Here it is zone 2. For this type of particle size, in this particle size range. But there, the heating rate is also quite high. Doesn't start until about this sort of heating rates. And zone 3 is all in here. In zone 3, as you would expect, everything, when the char particle has been completely heated, it will very, very quickly rise in, it will be heated very quickly, and it will be combusted very quickly. So that's how we read it, that in here, this is the ignition of the volatile matter and the particle itself, and in here, it is the ignition of the particle, just the particle itself, when the volatile has combusted and has given the enormous heat release for the particle to get heated quickly. Yes, this is only for the char. This is for the char and the volatile matter, and this is for the entire this thing in here. So as you can expect, when the particle size is very large, that's why everything will be in this zone 1, then it gets slightly reduced, then it will be here, and it gets more reduced in size, giving up its heat completely, and in the process got heated up. This is this will be in this zone. Where it is useful for the engineers is actually if they cannot make a quick determination based on the proximate analysis and the ultimate analysis and this ash analysis, if they cannot make a quick indication of how the coal is going to behave, they then start looking at this sort of graphs. But otherwise, it's very, very rare to look at this sort of graphs. These remain in the realm of the academic research. No, only from the laboratory testing. So for the designer, they get this analysis from laboratory testing only. Very small scale, well-controlled condition. So if they see that they have within their boiler designer, within their database, everything falls within their available range, this one, and this as well, they don't bother about looking at. But if they see anything, any of these values, significantly different from what they have in their database, that means they don't have any existing experience to fall back on, they then start looking at this. And then 2 more slides, Shantanu, and then we'll go. So this is again another slide with the volatile matter on the x-axis and the ignition temperature, depending on how much oxygen you are giving to the particle, because sometimes the oxygen comes with the air. So the oxygen gets used up. So the oxygen level will gradually decrease as it goes from the burner through to the exit, and at the exit finally you will have 4% or 5% excess oxygen. Depending on whether the combustion is air combustion or oxy-fuel combustion, which we will deal next week, the particles can experience either this type of oxygen concentration or this type of oxygen concentration. the important thing to note in here is that if you have more oxygen available, then you will see the ignition happening earlier at a lower temperature, which is good. That means it will fly. But if you have less oxygen available for whatever reason, then the ignition will be happening later and later, which means your boiler will have to provide more time. And equally important is the rate of ignition, at which rate it ignites the particle, the char I mean, and what is the ignition velocity. Again, these are very important indications that the engineers look for if they cannot make a quick determination based on what has been available to them. I think I will come back to this after a short break. Okay, so let's, I think we got another 2 slides left in this section. So we were discussing the char combustion after the ignition has taken place. And the char conversion or burnout, that can take place through all sorts of different reactions, depending on how much oxygen is there in the vicinity of it in the boundary layer, and how much oxygen can penetrate, diffuse through the boundary layer into the particle core. And some of these reactions can be heterogeneous reactions. That means solid and gas reacting together, or some can be just homogeneous oxidation, homogeneous reactions, depending on whether they get to both are in the same phase. That's why homogeneous. The bottom line is this particular expression in here, the rate at which the char can combust. That is often the slowest step amongst all the 3 other steps: the moisture release, the pyrolysis, and the combustion. The 3. So the rate of char combustion, engineers typically use this type of expressions, where A is the surface area that is accessible to the oxygen, which can be measured through temperature programmed desorption or temperature programmed reduction as well. Then this is an Arrhenius parameter, and this is the partial pressure of the oxygen that is available. So the experiments can be done in a very controlled condition in the lab in very small reactors. It used to be done quite a lot, say 30, 40 years ago, to get a feel for how much time the char will take to combust. No longer it is required, because over the period of time so much information has been generated in the database that whether the char is coming from biomass or coal of this type or coal of that type, this information is readily now available to whatever boiler designers or boiler manufacturers. But fundamentally, this is how it one can emulate it and one can calculate it. It's actually very fast. It's very, very fast. So it's not really any important anymore. As much important it is for gasification, but for combustion it is no longer important. But fundamentally, if you want to know how quickly it will combust, this type of experiments, this type of expression, knowing the K value and what this K total is, I will come to the next slide. So, in effect, we are still talking about the combustion of the char particles, but if you look at the reactions that have been shown, this is the predominant. There are in between these reactions, there are varied purposes, now scientific curiosity, but you really still need to read it, understand it. But the bottom line is this type of expression that you can calculate how long the carbon particle or the char particle will take to combust fully, provided you know the partial pressure of the oxygen, provided you know the active surface area to which the oxygen is available, the surface area accessible to the oxygen, and that can be measured, and the total K value, and that total K value depends on this type of considerations. So here in the y-axis, we have the inverse of absolute temperature, and here on the y-axis we have the rate constant expressed on the logarithmic scale. So there are 3 different zones through which the oxygen gets in to the surface through the boundary layer, reacts with the carbon, and then goes inside, and then goes to the pore, and then does the actual reaction. So there are 3 different regions. If you do the such experiments and draw this type of plot, you will see this type of figures, where in 3 different distinct regions, not necessarily every time you will see straight lines, but more or less straight lines with some scatter. So in this region, which is the truly chemical reaction control, that means the oxygen has diffused to the boundary layer, has gone inside the pores, and then on the active surface area is reacting with the carbon. That's where the chemical reaction taking place. There, the rate constant is proportional to the activation energy and the RT, the gas constant, and the absolute temperature. And here it is half of that, E/2, and here K is proportional to the temperature raised to the power of 1.8, so it's less than that. So the point is, because in combustion reaction, char combustion reaction is so fast overall, all these 3 things happen in parallel. So the K tot that we saw in here is actually a combination of the K's coming from these 3 different regimes added together. So again, it is more like a scientific understanding sake it is important, but for design purposes, this is the most important expression. So what they do is take a piece of coal, or the piece of char rather, certain amount of char, hit it with oxygen, measure the oxygen content at the outlet, so that you know how much oxygen you have given, how much is coming out, so how much oxygen has been consumed, and then you plot the yes, that's right, or it can be done in a flat flame burner, flat flame burner as well. So what you do then is you can then take an Arrhenius type of expression, A exponential R over E over RT, and then you start plotting the weight loss as a function of the temperature, or the inverse of temperature in this case, and that's when you will get this type of thing. What I might do is, because you were asking, I might give another slide giving the background of this one when I send it to you. But the important thing is to note is that this is the major expression that one is important, the designer wants to know. This is measurable, this is also measurable from analysis. This can be calculated from this type of experiments, for which I will give another slide. So sometimes what happens if you have a modular experimentalist combination, the experimentalist can actually do this for you through the experiments, and you then take it. But in reality, you will not get a huge difference between coal to coal when you come to char oxidation or char combustion, because the process itself is so fast. For engineering purposes, You will not see much difference. Yes. Okay. So let me clarify one thing. If you have a very high ash coal with little carbon in it versus another coal with lot of carbon in it but little ash, this curve will be different. Absolutely. So in that case, you'll be much better off to carry out these experiments. Correct. These are interrelated. Okay, so that's a very good point that you have raised. So if you have a lot of minerals in it, that means high ash coal, then the active surface areas will be a lot less proportionately. Because what's the active surface area? Is the surface area available to the oxygen on the carbon surface. The minerals are not going to react with the oxygen, but the minerals are impeding the access of the oxygen to the carbon, right? So that way, yes, absolutely, mineral matter has a consequential effect. The structure also has a consequential effect on it, and that way it is. So different coals, if the ash contents vary significantly, 2-3% ash content variation is not going to make much of a difference. But if it varies 12, 13, 20%, it can, then obviously this will have an effect. So you need to know the active surface area. And active surface area determination is done from temperature programmed desorption and reduction experiments. Yes, that's right. The internal surface area is what is most important. The pore is the surface area inside the pores, and when we have the lecture on the gasification, we'll talk about the pore surface area determination. So sometimes you can determine the porosity through the mercury porosimetry. So that will give out the macro surface area, if I may say so, because mercury molecule is very, very large. You can do the nitrogen surface area measurements or the CO2 surface area measurements. Nitrogen surface area measurements is done at room temperature, so the pores remain as pores. CO2 surface area measurements are done at cryogenic temperatures, and the pores can collapse. So, sorry, the other way around. So depending on which one you are using, you will get a relative number to get the active surface area or the value of the active surface area. And all of these techniques are complemented to each other. I will talk about that in the gasification lecture, because that's when it becomes very, very important. But one other thing that happens, let me also make a point. You can have a high ash coal and a low ash coal. But the coal particle disintegrates very, very fast, even though it is going into the furnace between 10 and 100 micron. And as I've shown there, they fragment as a consequence of thermal shock very, very quickly. So the discrete mineral particles go out this way, that way, and what remains accessible is predominantly the carbon to the oxygen. So that's where the high ash, low ash effects somewhat cancels out. And this is just a standard depiction of how the oxygen concentration profile changes from outside to the core. Obviously, the oxygen concentration will drop to 0 as it goes from outside boundary to the inside of the core. These are very important aspects for establishing the models, get a feel for how long, what's the length of the boundary, what's the dimension of the boundary, and that way. And for better mechanistic understanding, of how quickly the char particle can combust. Practical reasons, you can perhaps not require all that much, but for understanding purpose, for mechanistic insight, these are fantastic. These are really useful techniques. So that's why you'll see that plentifully in journal papers or PhD thesis, etc. So the total rate constant K taught in the previous expression, this is how this is determined from the individual values. And what engineers, as engineers, what we need to know a little bit more about is the typical burnout time as a function of char type and particle size, and that's therefore this is interesting. So if you particle size, the starting particle size is this much. So up to 300 micron, for example, starting particle size. But then, what is the starting particle size by the time it has gone to the highest temperature? That's debatable, because they are no longer the same particle size anymore. But what the way it I interpret is the y-axis here is burnout time. If this is my starting particle size, then typically the high reactivity, low rank coal will require less burnout time than the pure char or the high volatile bituminous or the medium volatile bituminous coal. So it is just a, we should not read anything more than this in here, that if I know my starting particle size, then as a function, if the coal rank is lower and lower, you can expect quicker burnout time. Knowing also at the same time, which is not captured here, is that the lower rank coals or the lower rank chars, they fragment very, very quickly because they are a lot less structured. They are a lot more porous compared to the high volatile bituminous HVB or medium volatile bituminous or bituminous coals in general. So that's how I read it. But again, important thing is here we are talking about in particle size, we are talking about the particle size as we feed it at the starting particle size. But the starting particle size quickly disintegrates into smaller ones very, very quickly, whether it is this or that type. And more so happens in case of lower rank brown coals. Okay. These two slides, I think I will discuss this in another presentation about the, why I did put it in here is that when we take char combustion, because of the temperatures, so the nitrogen also, what happens to the nitrogen and what happens to the sulfur. These are the two main polluting species. Apart from that, of course, there are chlorides as well present in some of the coals. But I think I will discuss that a bit more in conjunction when I discuss the gasification, the gas cleanup, those areas. So I'll skip that. But while the memory of ash behavior is still fresh, let's move to the next one, which is on the second part of the topic, ash combustion and ash formation. So it is here. Yeah. Okay. So here we are talking mainly about this phenomena in here, because that affects the coal combustion, whether this is advanced coal combustion or conventional coal combustion. Still, it affects significantly. And that's why I want to spend a bit more time on this. So my presentation outline in here is about the ash deposition, how I am defining it, how it is defined rather, what are the types of deposition, where it happens, what are the mechanism, whether there are any indices that you can predict from standard ash analysis, etc., and how you do it, how you can mitigate. So this is a this is quite important, and I will also talk a little bit from my experience on ash deposition in the circulating fluidized beds, because I commissioned the first circulating fluidized bed in Australia. But some of this combustion kinetics on circulating fluidized beds will be dealt with by Professor Sujoy Shah when he comes for his lecture, the fundamental side of the things. So I am actually jumping a bit, if I may say so. My understanding is that he will not be covering the ash deposition, because he will be covering more on the fundamental kinetics. So this is more or less this we're covering. Again, this is the diagram that we showed before, and everything that happens here is related to this part of the topic, ash deposition, because as I said, coal converts to char, then that converts to ash here, and then starts the phenomenon or the problems of deposition. And that's a very, very important part, and sometimes it is a very difficult part of coal-fired boiler management, operational management of it. So therefore, understanding the basics of it is important. So here we are dealing with only that part, nothing this side, nothing that side. So what is ash deposition? It is essentially release of the ash forming mineral matter in the coal. So after drying, after pyrolysis, after char combustion, everything. But the important thing is that these are very, very sticky at high temperatures. They really act as a glue, and you will see some of the figures. Transformation of those mineral matters, that's also happens very quickly, because some of the temperatures that you have seen, 1600 degrees Celsius, some of the compounds, they melt at very low temperatures, especially the silicates. And if you have sodium in its matrix, it will melt even at lower temperature. And if it is all present in a reducing environment as opposed to oxidizing environment, then it melts even at an even lower temperature. And sometimes in the vicinity of the particle, when the carbon in the particle has eaten away all the incoming oxygen, you essentially have a reducing environment, because you have the steam in its vicinity. So there, the ash deposition problem can become more aggravated. So transformation, and therefore the mineral matters transform from amorphous compounds to the crystalline compounds. They develop low temperature eutectics and all sorts of things. They are affected also by the size and the composition of the mineral matter in the first place. So when we talked about in here, they are through the X-ray diffraction, and sometimes through the, not sometimes, through the scanning electron microscopy, you can actually literally find out the size of the, and the composition of the mineral matter or the ash particle inside a coal particle, or the char particle, or an ash particle overall itself. You can literally see it, and you can literally pinpoint and find out what it is composed of. It is also affected by the local temperature, as I have mainly told you, that is, the reducing conditions can exist. Gas flow pattern, which means the local hydrodynamics and local gas composition. The local hydrodynamics is very difficult to predict, because when you first start a cold startup, the boiler may be clean, absolutely clean. So the hydrodynamics there is very well predictable, as is originally envisaged, but as there are more and more deposition, the surface becomes irregular, surface becomes rough, etc. Therefore, the hydrodynamics of the gases going through it, the hydrodynamics will be different, and that can affect the further. It can either aggravate or it can different gas deposition forming patterns it can create over there. So if this problem becomes more and more problematic, if you switch away from the design coal with time, as plants are sometimes forced to use new and possibly poorer grade of coals over a period of time, say 15, 16, 20 years down the track. So those are all unpredictable, and that can create problems, aggravate the problem of ash deposition. Okay, so number one. So we have seen in that particular diagram that these are typically you have a throat in there, and then it goes, and so this is, if you like, a very simplistic way that I have redrawn in here, and these are as if the multiple opposed burners. So, so where ash problems do happen, let me go one step back. This is about coal utilization. Coal utilization cannot be efficient if ash deposition problem is not understood or is not managed. That's why we are discussing it. So it's not just a scientific curiosity region. So this is where the bottom ash should come down if everything goes to plan. So, but not everything does go to plan, and therefore this is where the ash hopper, the bottom ash hopper, it can breach, the ash can form in here. So that's number one location problem can happen. Number two is that these are the ideal places for the ash to deposit, depending on the type of the material, its dynamic angle of repose. It can deposit here in the slopes. It can also deposit near the eyebrows of the burner. So you have one burner there, one burner there, one burner there. In between, there are nice little cool spot for the ash to form and then create all sorts of nuisance. Then you can also have slag. This is just over the burners, if you like. That's where the fireball is. Temperature is very, very high because char is burning. Volatiles have released enormous amount of heat, and therefore I am calling it slag. I am not calling it anything else. Slag means it has molten, possibly. Then in the middle as well, sometimes it can happen if you allow it to grow too much. Then just near the fast Platen superheaters are, so there are Platen superheaters, there are pendant superheaters, and then you have the reheater, then you have the economizer. Economizers are more or less in here. So this is the superheater region where also there is nice surface available, superheated surface available for the ash to deposit. Then you have the convection pass as it goes to the horizontal section in this towards the second. There also, because the gas is winding its way down, so they can separation can take place, the particles, and then they can deposit the ash particles. Then, of course, the economizer, where the temperature has cooled down, so sometimes if the ash is allowed to build up and not cleaned either by using the wall blower or the retractable steam blowers, then they can build up and they can cool down and they can solidify on the economizer surface that will impede the heat transfer. So, and then finally in the outlet, the air heater inlet, the cooled gas, there also fouling can happen because these are all happening by the fly ash. We are not talking about the char anymore. There may be a little bit of unbound carbon in it, but that's not the purpose of the discussion. So these are the predominant areas. Nothing, just to looking at two different ways. So fly ash. The fly ash is not light in weight. Fly ash is almost 2.5, 2.7 specific gravity. It's quite high. If you allow it to settle down, if you don't cool it. So every shift there are so temperatures are very well monitored. From the control room you should be able to see. But the boiler manufacturers will tell you that this is the way to manage the boiler. That there are some wall boilers which are fixed, either air or steam blowing. There are some retractable steam boilers which can go in and get out, go in, inject the steam and then clean the opposite side. And then, so that all depends on their maintenance. And I have seen all sorts of horror events where there's all available but no one bothered to operate. So I don't want to name, but I have seen this a few times in my career, both here as well as other countries in Thailand as well. Anyway, let's not say. So everything can go well. It's just about like maintaining your car, knowing it very well, and then maintaining it accordingly. If you don't maintain, this will also misbehave as will your own car. So nothing. So this is a different way of looking at it, different side, nothing else. So, so these are the 9 major areas. So the ash bridging. So the first one, it's essentially it happens because of the slag running down the wall, and then during the process solidifying. If you are not allowing it to flow down or not cleaning it, these also have large sinter deposits falling from the top of the boiler sections, from the plate and superheater region. There will be growth and growth and growth and growth, and at certain times they can just drop. This is very, very unpredictable, but more typical of coals which have very high iron content in its mix. I forgot to write in here Fe2O3 ash composition. So I will show you some of these samples, photographs of samples of very high iron containing ash and very high calcium containing ash later on. Ash slope, the problems that happen in the ash slope is reason similar to the ash bridging. Burner eyebrows, where it happens is it forms above or below the burner mouth. And what it does is it distorts the flow pattern. So you can predict the nice flow patterns from computational fluid dynamics calculations, but then what will happen is if you are not cleaning away this growth, then obviously the flow patterns will change. This is difficult to predict despite significant modeling effort. It really you need a very, very thorough understanding of the boiler, and it's a close cooperation between the modelers and the plant operators, and they often don't mix together very well. And these are very more coal and plant specific. Wall slag near the radiation zone, near the where you have the fireball, with coals having low ash fusion temperature or high heating value, and depends on the size, core size, more localized deposition. What I mean in here is that if the composition of the ash in here, if it is predominantly silica and alumina, nothing will happen to it, because these two compounds, they melt at very, very high temperature, and the PF boilers will never do anything to it. Fantastic. But small amount of calcium oxide, sodium compounds, and Fe2O3, which I forgot to write completely, they lower the sintering temperature and the melting temperature very much. So these are the ones which create the majority of the problems: the sodium, the calcium, the magnesium, and the iron. And to a lesser extent, phosphorus, that also creates problem if it is present. And then the number 5, which is right in the middle, which is specific to boilers having internal division walls. Certain boilers, depending on the manufacturers, they have actually an internal divisions. So that's where this can happen. Otherwise, majority of the boilers, it doesn't happen. And then the number 6, which is right on the platen superheater in the vertical first leg, but in the middle, that's when in 2 platens build up towards the bottom of the platen, and then gradually build up over and over and over, higher and higher up, and they harden with time if they are not cleaned regularly. Then the convection bank, so going into the horizontal section, mainly these are alkaline and metal sulfates, and they can be very corrosive if not removed regularly. The deposits in the economizer section, it can be severe for coals having high level of calcium in the ash. Okay. And if any other compounds are present, then it can become even more problematic. And of course, the air heater gas inlet, the last one, the large particles, if they get dislodged anywhere during the soot blowing. So what happens is we have a boiler, and then you have the retractable soot blowers from in here. They can go in and they can run the steam for a minute or so. These are all automated. This can be all automated these days, not only these days, right from the beginning. So the deposits which get dislodged as a result of this steam blowing, they have to get out somewhere. If they get out from the bottom ash hopper nicely, that's fine. But if they create small fragments which fly away in there and then get dislodged somewhere here and there, then it will be a problem. So that's what it is, the air heater gas inlet. I would say that items 3, 4, and 7 are by far the most disruptive ones, which for which books have been published. Literally, books have been published on small lab scale experiments through to the real online sampling done in large boilers. So, here, let me talk about a little bit more about the slagging and all. So, say this is the tube wall, and on other side you have another tube wall. In between you have the flame. So, what happens to the flame as the gases laden with coal and the ash particles, or the char and the ash particles, they go up. Part of it, the incident radiation from the flame, is reflected. Part is emitted back, absorbed, and then emitted back. Part of it is convected, and then it conducts heat. After overcoming all of these things, whatever heat goes to the steam inside the tube, the water inside the tube to generate steam, that's what happens. So if you have a deposit build up in here, and if you don't know how it is building up, the mechanism is, then you got a problem, because you will not be generating your steam at 600 degrees or 650 degrees or whatever temperature you want to generate the steam at, depending on supercritical or otherwise. So the effect is that it reduces the heat exchange, it reduces steam raising, and as a result, it also increases the furnace exit gas temperature. Because if the heat is not being taken up by the water as a consequence of the buildup in here, the heat has to go somewhere, so it has to go to the top and the exit, and there the temperature will slowly go on increasing. So furnace exit gas temperature measurement indication is a very important measurement that any plant operator sitting in the control room will always keep an eye on, and that is logged in seconds. Every seconds. They need to look at the trend over shift and over shifts. If that goes increasing, problems are happening. And then as a result, if it increases the surface temperature, then the particles tend to become sinter. Eventually they will melt. That's natural. So, so this was from my PhD time. We did with Terry Wall that what we're trying to mention in here is that you have the clean tube to start with, and then eventually how these deposits actually grow, that we postulated and then proved that postulated theory, that you first get a deposit on the clean wall. We did it at the Eraring pass tension, I think, at the time. And the fine ash layer is deposited, and then the temperature eventually the heat transfer drops. So with time, there is a growth on the deposits, and then that consolidates, and that then matures. And if you allow that to happen, then everything will run away, and then you will not be able to get the desired performance. So this is what we postulated at the time. But the mechanism through which there are two different ways of ash deposition that our ash deposition is classified. One is fouling and one is called slagging. Slagging means that everything has molten, and which is not, which means there is a very, very high temperature. The other one is fouling, which means it's not molten, but it is fouling. It's just depositing. So it's a lower temperature, so less than melting. So ash deposition is classified into slagging and fouling. And slagging means slagging happens where direct impingement of the flame is taking place. That's in the radiation zone, right near the burners, where you have the hot flame. And then the fouling switch, where the area is not directly exposed to the flame radiation, but these are the processes that eventually leads to the deposit. So you have the tube in here, the fine particles fast deposit. They then attract the more and more into the more and more of the dry ash particles, and then eventually the temperature here rises because it is impeding the heat transfer to the water, and therefore then it starts to become slag. And if it grows too much, then it can shed and drop, but if it doesn't, then it will simply melt. You don't allow that situation to happen if you can, but that depends on the operational management during every shift. So slagging is a function of the surface temperature, which is often measurable. These days you have the optical pyrometry. Clearly it can measure the temperatures. The flame temperature itself, it is also determined, is a function of the heat absorption rate by the water, which becomes steam. So if you see a drop in the steam temperature, which is measurable at different locations, then you know it's problems happening. It also is a function of the direction of the gas flow. If the gas can flow in that path as a consequence of the deposition, then there will be hot areas and cool areas, and that will create the problems. Then obviously the mineral composition, size distribution of the coal itself is a very, very important determinant. If the milling system or the upfront coal preparation system is not giving you the size of the particles prepared to design specification, that often is a problem too, in addition to the coal being changed significantly from its design condition. Oxygen level in the flue gas is another one. Oxygen level in the flue gas near the slag surface. So there can be localized reducing condition if sufficient oxygen is not present, and reducing conditions, some of the compounds, they actually melt at a lower temperature. So this is a mechanistic insight that Terry Wall, my supervisor, and others, they postulated how from char particles to the volatile inorganic vapors, and eventually how it goes into the heat transfer surfaces. What are the processes that takes place, the nucleation process, the thermophoresis, etc. They have a fair number of publications that were available in the early 90s, but these are nowadays, no one does it anymore, simply because these information are so much readily available to boiler companies, whether it is BHEL or Hitachi or you name it. Everyone now knows all of these things, but there was a time when we had to develop all of this information. This slagging is also important, is affected by the presence of the concentration of the iron or sodium and calcium in the ash. So knowing this, therefore, the knowledge of the ash composition is very, very important for the boiler designers. They can easily make their first impression. If only iron is present, then it reacts with the aluminosilicate to form the low melting or low viscosity eutectics. That means, so what I mean is that the minerals which are present in the coal to start with, they can be all sorts of things. They can be clay, the clay is, as you know, as soon as it hardens, it loses the moisture. And then if there is any temperature treatment applied on it, then it hardens even more. So clays are present as aluminosilicates in the coal as minerals. So if only iron is present but not calcium, then they react with iron aluminosilicate they make, which is quite low melting. In its own, aluminosilicates do not melt at low temperatures at all. Nothing will happen. But it's a tiny amount of iron that is present can create havoc. And on top of that, if calcium or sodium is also present, then it creates even more problem. So it creates a sticky surface on the boiler tubes, and sticky surface traps the incoming particles, the ash particles, and then they will grow. So this is essentially a schematic of the slag buildup, if you like, from the tiny ones, how the bigger ones can grow, and they can grow and grow and grow, and then surfaces can become completely covered if you are not paying much of an attention to it. The fouling is slightly different. Fouling is not in the high temperature zone inside the furnace. It is where you have the reheaters and the economizers, that area, downstream. So there, typically it is initiated by a thin layer of the condensed vapors of the alkaline species, hydroxides and of sodium, chlorides, etc., which are, if they are present, sodium sulfate as well. So I have written in there. And then it reacts if also sulfur is present, and sulfur gets converted to sulfur dioxide, the organic sulfur of it. Let me digress a little bit. When we determine the sulfur from sulfur in the coal through the different elemental analyzers, we usually determine what we call the total sulfur. But that total sulfur can consist of three types of sulfur. One is the organic sulfur, which is very loosely bonded with the coal matrix, and therefore this will just go off as temperature increases. It will detach itself and it will give you sulfur dioxide. Then you have inorganic sulfur, which inorganic sulfur means it is bonded to the other coal minerals, calcium or iron or sodium, etc., difficult to dissociate. So that actually forms the sodium sulfate or calcium sulfate or iron sulfate or a mix of those sulfates. So that's the inorganic sulfate, the fate of that inorganic sulfate. Then you also may have, not always, pyritic sulfur, FeS2. And if that happens, then you've got a problem. So often there are ways in power stations with a high amount of pyritic sulfur to actually remove the pyrites during the coal preparation stage, because that is a very, very problematic one. So that you are otherwise only organic sulfur, not a problem. It will go out as sulfur dioxide, and then you can capture it using the desulfurization unit downstream from the flue gas. And if you are careful enough, you can get some good sulfur to sell as well. So, so that's basically it. Then the next one. So if I go again, so what I have said in here, that the slags will be forming predominantly in the just over the burner surfaces, and this is where the fouling will be taking place. And there the fouling is because of the sulfate bonded to sulfate from the calcium or the sodium, etc. And the slags in here in the middle are predominantly because of that. So that's the summary of what I have said. If we try to, this is what happens. If we try to look at a little bit more mechanistically as to how this happens, even though I have mentioned before that the ash has to come out. The mineral matters have to get converted, which does get converted. That has to be transported to the tube surface. What does that is the gas velocity. And you need very high gas velocity because you need a small boiler because everything is so fast, but that has a consequence. In a typical boiler, the gas velocities are of the order of about 10 meters per second, so it's not small at all. That has its pluses and its minuses. Pluses in the sense that if properly managed, it can take away, remove everything. But if it is the gas velocities, they change as a consequence of the mal-operation or mal-management, and therefore the gas pattern, flow pattern changes, then you will have places where the gas velocities will not be uniform. In some places it will be too much, in some places it will be too little. And that's where you'll start creating the situation for this problem. So it depends on the physical state of the ash, whether the ash is solid or the temperature has gone so much higher that it has become liquid, or even higher that it has become vapor. It can happen. They are chemistry. So what is in here? If it is too much of iron or too much of calcium or too much of sodium, too much of magnesium, etc. And the flow pattern of the flue gas and its composition. So there are four principal mechanisms. Of course, the first is the inertial deposition, then the vapors depositing on the tube, then it is condensing there because inside the tube you have the lower temperature water, so it is condensing immediately. As it is condensing, it is also becoming sticky, and if you are not cleaning it away, then it will attract the other ash particles to come and bond to it. So that's what is written in here. This condensing, then the thermophoresis driven process can aggravate it, and as a consequence, the temperature in the deposit, particularly at the surface of the deposit, will be increasing because it's not even able to give its heat away to the water. So chemical reactions, the mineral transformation reactions taking place, that's what it means. And then all of this give rise to the stickiness of the particle. But not necessarily all of this at the same time are responsible for slagging or fouling, but some of those, sometimes all of those do affect the these deposition problems, classified into two major types, the slagging and the fouling. So the 5 bullet points that I have in here: inertial deposition, that's what I'm discussing now. The inertial deposition is the more common for larger particles greater than 10 micron if they are present. These will predominantly come from the minerals. Their impaction rate highest at the leading edge. As you can imagine, it's coming from in here, and at this edge it will be leading. It will be impacting higher, and then obviously surrounding it, it will slow down. And then the condensation, it takes place where the vapors pass over the cool heat transfer surfaces. They tend to form a thin layer, but they can be very, very sticky depending on what the vapor is consisting of. If it is consisting of predominantly sodium and the calcium ones, they will be very, very sticky. And then the thermophoresis, it's a consequence of the, or it happens because of the steep temperature gradient between the flue gas and tube surface, because you have 1500 degrees or 1600 degrees temperature in the flame and 500, 600 degrees inside the tube. So that's a huge temperature gradient to allow thermophoresis to happen, and means sharp changes in the composition of the particles as this temperature difference and this migration happens. So there are thin layers, very fine particles creating thin layers, attracting larger particles, and then it is allowed to grow. Everything happens if the cleaning system is not properly operated. If it is properly initiated, and if everyone knows that the cold change is taking place, then these problems are manageable problems. These problems only run away if the boiler is not managed properly. So before I go to the next slide, I think I'm hurrying it through. I'm looking at some of the faces. It's clear to me, but is there any question before I go to the next slides? So it gives me the opportunity to have some drink. No. So maintenance, there is boiler maintenance. There is called scheduled outage. Scheduled outages are all defined by the boiler manufacturer when they sell you the boiler. They tell you that, look, after X thousand hours of operation, there are 8,760 hours in a year. After X number of hours of operations, stop the boiler, clean it wholesale. Then the other one, is the most important one, is the during in-shift cleaning. And for that, one has to know the temperature gradients. One has to know the temperature indications inside the different parts of the boiler from the control room. If the control system is working very well, if there are telltale signs of problems, then you decide to either shut down the plant or reduce the load and clean them. But there are strict regimes for every shift cleaning of the operation of the soot blowers, the wall blowers, I mean, which will send in steam and clean the deposits. If that doesn't happen, then problems take place. Good companies, they run brilliantly. Not so good ones. Strongest indications. Correct. Vibration of the tubes is not necessarily an issue. I don't think vibrations can be detected. It is the sudden changes in the temperature of the steam. That means sudden temperature changes in the furnace exit gas temperatures. Those are the indications of problems. And not in, it's impractical. But these days, you know, you have optical diagnostics. People have their operators, they work with the handheld temperature detectors. They can go and open one of the furnace doors, small furnace doors in the aqua, after meeting all the occupational health and safety regimes, and then calculate the temperature easily. And that does happen. The diagnostic systems, handheld diagnostic systems, are very, very sophisticated these days and common these days, and very cheap as well. Whether that happens or not, that depends on who is owning it, what is the impedance of it. But the point is, the purpose of this discussion is to know what creates this problem. How you solve it is another. That's the management strategy. Okay, so the deposition mechanism, the chemical reaction. Chemical reactions partly it determines if the particles will stick or not. Once they arrive at the surface, there's common sense, nothing spectacular in it. Formation of the low melting point eutectics, low temperature eutectics from the interactions between these species. The aluminum and silicon compounds on their own, alumina and silica on their own are fantastic. They will not create any fouling problems on their own as such. But it's these bits, these are the naughty ones, which creates problem along with this. And of course, sulfate as well. And if you have high alkali coal or if you have high chloride coal, depending on where the coal is mined from, it can obviously you can have chlorides as well. If you have tiny amount of sodium chloride in the deposit, it can melt at 600, 700 degrees centigrade. which is extremely low. So again, the point I'm making is, not often, the core companies actually do tell you. Apart from this, you also tell us how much is this present. And that's not part of the ultimate analysis at all. It's not part of that 100. It is separately asked for, if it is a salty coal or not. If it is a salty coal, you need to wash it out. So the stickiness of the particles, again, that is dependent on the chemical reaction. It depends on the size of the particle. Obviously, if it is a smaller one, then it will stick faster, as you can imagine. The velocity, if it is low velocity, it will go and sit on it, not get dislodged. Angle at which it is impacting. So all sorts of things. Viscosity of the liquid film. It's very, very difficult to measure that actually, even though you can predict to some extent, but these predictions are predictions. And when we, one of the modules we have effect of ash viscosity on gasification, gasifier design and operation. I will show it to you. We did this big project for Mitsubishi and Japan Power. It's a fascinating field which is still developing, purely because the experimental, the current models do not work, and the experimental work is extremely difficult to perform. But I will say that, so the point I'm trying to make is, this is obviously, if it is very, very viscous, then as liquid film which is developed, generated on the tube surface, will nicely flow away. But life is not that simple. The viscosity can change widely depending on what is there in the compound. This viscosity I'm talking about, the viscosity of the ash forming on the wall. I'm not talking about the viscosity of the liquid water inside the tube. Ash viscosity. Okay, so as I said, if ash deposits, then what will happen? It is creating an insulating barrier for the heat from the flame to go inside the tube and change the water to steam. So heat transfer is impeded. As a result, the heat has to go somewhere. So what the heat will do? It will increase the temperature of the ash deposit. And if the temperature of the ash deposit keep on increasing, ash will simply become molten. But if it is molten well enough, and if it is viscosity is if it is low, then not a problem, it will flow. If you can predict that the viscosity will be low, then it is even better, because then you will say to your engineers, let them grow, it will flow away. That's the principle with which the entrained flow glass gasifiers work, that you maintain the viscosity in an entrained flow gasifier between 25 and 150 pascal second, PAS. Without digressing, the point I'm making is that if you have a molten layer of ash whose viscosity is low enough so that it falls away, then that's not a problem, because it will grow, but it will melt and it will fall. But if it doesn't fall because it is extremely viscous, then you've got the problem. So we are talking about the ash viscosity. Ash is like any other compound. So in viscosity, we typically align ourselves to water, liquid, right? But in real life, we have ash also can have viscosity. We measured ash viscosity at 1600 degrees centigrade. It's a big challenge. We'll talk about that later on. So these are some of the figures that I have taken. That critical viscosity is between 10 to the power 6 and 10 to the power 7 poise. That's sometimes the design engineers, the boiler designers, they actually look at it. And where they get it from established models, in-house or otherwise, from this composition. So if you give them this ash analysis, they can calculate what the viscosity is. And if they see that it's beyond the critical range, then they will say, look, there will be a problem, so you have to have mitigation strategies to avoid or minimize the deposition problem. Yeah. Highly viscous. So it will not move anywhere. It's not going anywhere. It's sticking. Yeah. Yeah. So, so what have I done? What have I written? So it will stick. So I should change it. Good. So you're not slipping. Excellent. Yeah. That's it. Very good. So I should change that. So then I am right. He's wrong. Yes. No, I think you are right. You are right. I think it will then particle will rebound if it is a highly viscous surface. But if it is a very molten and flowing low viscosity surface, then it will not rebound. Absolutely right. So it will stick and stick and stick, and then it will grow. So but eventually the point comes to is that that then becomes where it becomes an issue though is that the viscosity becomes so much unpredictable, even with the slightest change of the composition of the layer, because at times you may have some less sodium, some high silicon, some high calcium, it becomes very, very unpredictable. So no one actually knows what is happening there because it is impossible to see during operation. So the important thing to ensure is that whatever the boiler designers say that look, every shift or every half a shift you apply, you do the cleaning to the wall blowers, knowing the problem will go away, that's what it should be done. Yeah. 8 hours. Yeah. Not 12 hours. I have seen some boilers, they are actually even recommending every 4 hours you operate the wall blowers. You can do it from the control panel. The wall blower. Wall blower means on the wall you have the steam injection points at different. So closer to where the deposition will take place, people can predict it very, very well these days from experience as well as computational fluid mechanics designed predictions. You operate, you put the wall blowers around those sort of areas, clean them. See, the other thing is, if the deposits are not cleaned, their absorptivity will decrease and their emissivity will change. And as soon as the emissivity changes, I mean, which can vary from 0 point something to 1 maximum, it will be emitting more and more the radiation or the heat back into the flame and increase the furnace exit gas temperature. So your steam tubes will be suffering. So, so that's another issue. So I'm not sure whether I've answered your question though. Too much of ash and the composition of the ash. If it is a high calcium containing coal or high sodium containing coal or high iron containing coal, then the problems will be different. But the problems are all manageable, provided you know why they happen in the first place. And the boiler designers, the boiler companies will give you the mitigation strategies when they sell the boiler. This is how you need to manage it. Don't listen to it, and then you are working you're to your peril. Any other question? Yeah. So okay. So say for example, you have bought pure silica, alumina, sodium hydroxide, mixed into sodium hydroxide, and some calcium oxide and some magnesium. You mix it at different proportions, and then you start looking at the deformation temperatures as you hit it. You'll see some are melting, some are deforming and melting at very low temperatures. So why it is because these components are reacting with one another. It's a solid state reactions that is taking place. So that's what mineral reaction is. So it's not a gas solid reaction, but it is this between the solids of different kinds, forming new compounds which melt at a much lower temperature. In agglomerated ash, it can exist as sodium sulfate, it can exist as sodium silicate, Na2SiO3, it can exist as sodium aluminosilicate, NaAl2SiO3, or NaAlXSiO5. So only Al2O3 or only SiO2 or SiO2 plus Al2O3 will not create any problems. They melt at very, very high temperatures. Those temperatures are not attainable in the boiler, but as soon as you have a bit of sodium or calcium or iron or magnesium or all of those present in it, they will start reacting to form a new compound and eutectic which will melt at lower temperature. So that's what mineral transformation means. And it depends, it varies with whether the condition is reducing or condition is oxidizing. So that creates a problem as well. But these are now very well predictable through the phase diagrams and thermodynamic calculations. You can actually get packages. FactSage, for example, is one. HSC chemistry is another one. To some extent, the database is not too bad. The FactSage, and then the Germans have developed another one. What's the German equivalent of CSIR in here? I keep on forgetting. They have developed their own packages now based on enormous number of laboratory experiments, mixing these minerals and creating different conditions, then measuring the composition of it after the reactions, and at the same time measuring their sintering temperature, their melting temperature, etc. You have optical microscope, hot stage microscopes which can detect these temperatures very, very well in the laboratory these days. Okay. So, have I covered everything? Yeah. And then the fouling, this another one is that if you have the different tubes and the very clean tube, not a problem, the deposition stages, and a little bit of, then it areas are more prone to deposition. I've shown 9 different areas predominantly. These are pretty well known these days. Important thing is to apply this soup blowing. If you don't, then you have problems. So your question is mineral matter transformation. What does it mean? Is the transformation of the compounds consisting of all of this, any or all of this. As I keep on saying, these two alone, they are not problematic. It's the other ones which creates and starts creating the problem. So how can you actually then control it if these minerals, included minerals in the coal, are very large size, and you can detect them through electron microscopy easily. Electron microscopy coupled with, say, EDX, energy dispersive X-ray spectroscopy. You can do it in the lab all the time. Nowadays, you know, the SEM scanning electron microscopes are only this size. They used to be during our time, let's see, this room size it will take. Now you can buy the desktop SEMs, $15,000 to $20. Very good enough, 50,000 magnification, you can do it. Anyone can do it now with 6-7 hours of training. So these are very well known. The problem is if the important information is that if you know the minerals very, very well, how big these are, if these are very big, then milling can clear them out. You break the coal through milling, and then the minerals have higher density. Silica alumina is what, about 3.5, 3.7 specific gravity. Silica is 2.5, 2.6 specific gravity. Coal is nothing, 0.8, even less than that. So density separation is very, very easy after you've done the milling. So one way of mitigating it that way, if you know it, can be done. But if they are organically associated, that means they are very strictly bonded to the carbon. It's very difficult to separate during milling because then you will be losing the carbon as well, which you don't want to use, don't you want to happen. So the point, bottom line in here is that the characterization is also important, very, very important. These days, analytical instruments are so easily available and so easily operatable that anyone can do. I mean, the students can do it all the time. Whatever. So, and then the role of calcium, I thought it will be very, very important to bring it up in here. Calcium can have a very funny role in the whole thing. Up to a certain point, calcium is a problematic element to have, but beyond a certain concentration, it can actually be helpful. And I'll show you some example of some of the problems we experienced at the main power station in Thailand and how that was overcome. So what happens is calcium is present mainly as carbonate, also as gypsum, and it can break down, as you all know, calcium carbonate. If you heat it at 800 degrees centigrade, it release the carbon dioxide. That's what happens in cement mills anyway. And then in the coal environment, it can then combine, this calcium oxide can combine with sulfur to give you calcium sulfate, which is low melting point. Calcium oxide can also combine with silica. It forms sticky calcium silicate, perpetuating deposition. It can also create problems together with the sulfates of sodium and magnesium, forms low melting eutectics. So sodium sulfate, I think it melts at about 880 something degrees centigrade, so very, very low temperature. If you have calcium sulfate in there, calcium sulfate alone melts at much higher than that. But if you have sodium sulfate, calcium sulfate, magnesium sulfate all present together, they melt at reasonably low temperatures, well below, in the lower range of what is expected, what is encountered in boilers. So these are actually more problematic. Calcium is more problematic for lignites because lignites have, in general, have more calcium than the bituminous coals. Iron is another one. As I have said, iron can occur as pyrite, or it can occur as marcasite. These are all different structures of iron. Or it can be present as just hematite or magnetite, or if it can be present as siderite. So it depends. So it's, again, these are all very well detected by X-ray diffraction in what form iron is present in. So you can say that if you can give these problems, if boiler designer says that, look, your iron content is problematic, appears to be problematic, just initiate this experiment analysis, give this information, and then further design strategy to mitigate the iron-induced problems can be devised. And here I have given why these are problematic, because they may decompose, starts reacting at decomposing and then reacting later on at a very high temperature, low temperature. And iron plays a very important role in slagging. If you have a low iron containing coal, slagging problem will not be significant at all. Sulfur is another problematic one. Occurs as organic, inorganic, pyritic, or marcasite, as we mentioned before. Organic sulfur is released as sulfur dioxide during char burnout. Pyrite fuses because it breaks down at low temperatures, and then it creates problem. It can react with the sodium, calcium, and magnesium to form sticky sulfates. And sodium and calcium sulfates decompose in presence of silicates, forming eutaches, which can melt as low as 752 degrees Celsius. So these are summary of minerals commonly found in coals. I have just copied it, photographed it from Rusk's book, and that's why it's a very hazy scan. I should have given the reference to it. It's a book by Rusk in the early 80s, RAASK. So these are some of the compounds present, identified through X-ray diffraction, present in the coal as minerals. So these are minerals actually. So there are all sorts of slagging indices. So we have talked about the problems. This creates this, that creates that. This is good, this is bad. Together with this, they create havocs, etc. So what the engineers do is, again, I have copied and pasted it from Breyer's book after hurriedly done for copying. So one of the ways to understand whether slagging will be problematic or not is to do the ash fusion measurement temperature, because that is then used to select the maximum furnace exit gas temperature. So if you get the ash fusion temperature, then you will design your gas velocity and design your boiler height in such a way that furnace exit gas temperature remains below this, so that it doesn't fuse there. The ash doesn't fuse, simple. Then the critical viscosity, temperature at which viscosity changes from Bingham plastic to Newtonian. So the Newtonian, any viscosity which is of a liquid which is Newtonian in character is easily predictable. But as soon as it deviates from that to non-Newtonian fashion, then that's when it starts to create problems. So there are some ways to measure the viscosities of the ash. We have done it. Extremely difficult, usually not done, but in the extreme cases, the boiler companies do warrant that sort of figures to actually done by actual measurements, analytical measurements. Then this is the most important one. It's not necessarily a very definitive one. The base to acid ratio. So here you have in this composition, ash composition, some are basic oxides, some are acidic oxides. So the boiler manufacturers do actually come up with a base to acid ratio, and from there they can say that, look, if the ratio is below 0.6 or this range or that, then the degree of slagging will be low or medium or high or severe. So base to acid ratio measurements, not a measurement, an index, in this index based purely on the ash composition measurement is widely followed, only if that coal composition is within the database of what they have, that means on which they have experience. If not, then ask for these experiments to be, the analysis to be done, the actual viscosities to be measured, etc. There are other ways of coming up with the slagging index. Some of these ones progressively actually are less important in my view, which are not followed, which are not exactly pursued by the boiler designers at all. They mainly look at the base to acid ratio. If not, they go for measurements in the laboratory. Very, very difficult and expensive, but that's what they do it. But the other ones are all, to some extent, I would say, academic interest. They give some indication, but not necessarily definitive, and not. I haven't heard of anyone actually following, any manufacturer following these ones, other than the top 4. And then the fouling indices. So those are the slagging indices. Then the fouling indices. That is a little bit more complicated depending on what the type of coal is. So for bituminous coal, this is for the American bituminous coals, the ASTM method was used to come up with this sort of ratios, and if the ratios are within a certain range, again they can say, the boiler manufacturers say that the fouling propensity will be low or medium or severe, etc. These two are the more interesting ones and very, very important ones for use with lignites. Those have lots of sodium compounds, lot of iron compounds, lots of calcium compounds, etc. And if they also are salty, in that case, these two, 5 and 6, are the good indicators. Again, these are predominantly thumb rule. They can never replace the need for actual measurements if the boiler designers cannot form a strict opinion based on their experience. So the new ones, the new players will be looking for this. The old established players, unless their information is available to the other ones, they will not ask for it. So the bottom line is in here is that the slagging and fouling, why it happens we know. There are ways to get engineering predictions whether the problem will be severe or not severe or manageable, and that the most important thing is the operational strategy. And the only operational strategy, irrespective of all of these problems, is two. One is either get rid of the minerals as much as possible if economics justifies during the cold preparation stage, during washing, etc., or manage it during operation. Then the characterization of the ash, the fusibility, as I said, the ash fusion temperature measurement. So this is a very standard method now. So what happens is they take a certain amount of an ash. The ash is prepared from the coal by burning away the carbon. They prepare a cone of using it. Ash fusion temperature furnaces are common. Many universities have it. So they prepare a cone of ash, and then they hit at different temperatures, and then the cone then gradually melts and melts and melts and melts and becomes like that. So initial deformation temperature is this, sintering temperature is this is the melting temperature. So based on this, the boiler manufacturer, and this is very simple, relatively cheap to do these days compared to the early 90s, I would say. And you can actually literally see what's happening. You can record it, and you can pinpoint within plus minus 5 degrees what's the temperatures are. Important thing then, it goes into the boiler design is, okay, I will not allow my furnace exit gas temperature to go anywhere closer to that temperature. So that's what it is. So the number 2 is initial deformation temperature, then softening temperature. This one is hemispherical temperature, fluid temperature. can be done in both reducing temperature and oxidizing atmosphere. Usually the boiler designers do specify. I have seen these days they all say give us both, because these temperatures under this atmosphere are actually lower than this, and they go very conservative. They do everything on the basis of these temperatures. Laboratory methods, the other analysis, the ash analysis, exofluorescence, ICP, as I mentioned before. Thermomechanical analysis is another way of measuring getting an indication of the sintering or the ash melting propensity. What it does is you take a sample of ash, you put it inside the container, and then inside the crucible you apply heat from the sides, and then you apply pressure. So that's why it is mechanical pressure with thermal heat from the sides. And as you would expect, if it is melting, the piston, the mechanical pressure exerting piston will be dropping. How much it drops as a function of temperature and time, that tells you what it is. So this is a different technique, but easily done. X-ray diffraction, X-ray mapping, scanning electron microscopy, computer-controlled scanning electron microscopy. This is viscometry, as I mentioned before. The other one is the phase diagram. And of course, nothing beats the thermochemical calculations. Nowadays, desktop computers, the packages are available. You can do the thermochemical calculations. The majority of the 2-3 GTT is the German one. FactSage is the front runner. Extremely expensive now to maintain the license anyway. So you can actually predict if you give an ash composition, tell the software in the input file what's the atmosphere is like, whether it's nitrogen or CO2 or any other reducing or steam. You do the calculations at different temperatures. It will actually tell you what the compounds that are going to form under reducing atmosphere versus oxidizing atmosphere as a function of temperature. So that will give you the first indication. And then, of course, the proof of the pudding is in eating. Then you take melt the ash fusion temperature furnace or optical stage, hot stage microscope, and then you take it and run it in the X-ray diffraction. These days you also have high temperature X-ray diffraction. So you actually put the ash there, and then the goniometer, it measures the diffraction pattern as the ash is heated. So we have done that a fair bit. Not too complicated, not too easy. Interpretation of the diffractogram requires a bit of knowledge, but there are experts on that area available. So the point I'm making is that problems are there, indices are there, solutions are also there. All it needs is goodwill and some effort to work, and of course, fundamental knowledge of it. That's what you all will be required to know this, and then so that you can tell the operator that, look, you need to do this. Don't shortcut. Okay. So, and of course, if nothing comes out from this, go for suck and see approach, trial and error approach. But that is easier said than done. Massive effort. And of course, the full-scale trials. But these days, these problems are easily solvable. I think I copied it from Breyer's, and Breyer's book is a very old book, so certainly I haven't done a good job in photocopying them. So they have before the ash fusion temperature measurements became mainstream, these were the ones that were used. I have just put it there, that how the knowledge has improved over the period of in the last 3 decades, so much so that no one bothers to look at this anymore. Even though historical perspective-wise, it's good to know that this exists, and it exists here. But the fact is now you have the analytical instruments to give you the pinpoint information without requiring to surmise anything from what our predecessors had to very painstakingly go through and do it for us. We now are the beneficiaries of the next generation of researchers equipped with all sorts of instruments. They give you some numbers, that's it. So the TMA, what it does is thermomechanical, how much more have we got? Oh, I didn't notice it. I think we took a longer tea. So give me another 5 minutes. Because I never go home before 7:45. So I think, no, I'll let you go quickly. Okay, so maybe 3 more slides, huh? I can go on? Okay, that's very good. That's very good. Because I haven't digested my lunch yet. Okay, so what happens is you temper, as I said, you take the ash, you apply heat from the sides, you then pressurize it from the top, and then you see these sort of signals coming in. And sometimes they start melting, and then reactions go on, and they form some other compounds, which becomes very, very hard actually. Don't know what it is. And then you start to get this sort of signals. Then another sort of transformation takes place between this temperature range, and then it develops a trough, and then it goes like a massive transformation happens from here. Now, what you actually get is not this one directly, you get that one first. Then when you take its first derivative, that signal divided by dt, whatever, then you get it similar to what you do get in the TGA instrument, those who use thermogravimetric analyzers. You get the TGA signal and take the dWdt, then you get this, the first derivative. The first derivative actually tells you where the transformations are taking place. It doesn't tell you what transformation taking place, but it pinpoints where it is taking place, whether it is large or sharp. And then, of course, you find it through the X-ray diffraction. So TMA is a fantastic measurement technique. TGA, DTA obviously can also do the same thing to some extent, but depends on the TGA. Not all TGA will be going to very high temperature. And then X-ray diffraction, but it only identifies the crystalline compounds. It detects the amorphous compounds as a blob, but without identifying what they are. Usually done at room temperature, usually, but these days high temperature XRDs are becoming more common. And then, of course, SEM, EDX, whether you are doing it in the secondary electron image or backscattered imaging mode. I don't know how many of you actually have handled SEM. Have anyone handled SEM? Okay, so scanning electron microscopy, the way it works is you have a sample in here, and you then bombard the sample with a beam. That releases, depending on the voltage that you are applying, that releases the electrons. And how many electrons you are detecting, that tells you what the actual compound is. So there are different ways of doing it. One is called a secondary electron image, SEI. The other one is the backscattered image. The secondary electron image, depending on the sample preparation, it only gives you the information from the surface. Backscattered image, it gives you from the bottom. So it essentially tells you what's gone in, because it is giving you the scattered electron coming from the other end of the sample. So between the two of those, it gives you fantastic information of what elements and what is the elements are present on the surface as well as in the inside. And then, of course, it gives you the morphology as well. EDX is another one. So you can generate nice pictures. As soon as you start seeing the spherical ones, you know that why spherical shape happens because of high temperature. So it always then immediately tells you that this sample has undergone high temperature. It can give you this type of very porous air. And you can do the EDX. You can pinpoint within a zone what its constituents are, that this is calcium or silicon or this or that based compound. It gives the elemental signal. And then you can, of course, you can do the X-ray mapping as well. And within the X-ray mapping, that you can see with the different color coding what compounds are present, what elements are present as compounds, whether it is predominantly calcium, iron, or sulfur, or together with silicon, etc. So the mapping does it over the entire surface of the sample that you are trying to analyze. That's why it is mapping. Whereas EDX is just point-based. But if you do sufficient EDX at different points, then it becomes representative of the entire sample. Phase diagrams is another one. I think I will stop at that point because of the phase diagrams. It will be a different set of discussions. So we'll start from that point tomorrow morning, and we'll have a